Non è in camera, quindi dovrebbe avere consiglio. Senti, uso le slide PDF per favore, perché uso le slide che ho uploadato, perché non trovo. Se viene con la mia busta nera, sì, ma non so se senza il power. O anche dell'USB-C. Sì. Di qua. Perfetto, allora il power c'è. Mi hai mandato il link?
L'ho mandato su WhatsApp.
Questo?
No, chiudi anche il video. Fai uscire. Gelato. Sì, deve stare molto vicino a tutti. Non è il massimo.
Però volevo togliermi quello stato lì.
Quello lo puoi fillare, vai qui come metti la prima.
Orario.
Io direi di andare dritto, così, non ovviamente magari a metà, fare... Okay, so we reconvene and we change somehow subject, so still phenomenology, but on the neutrino sector. Lecturer is Professor Marco Pallavicini, University of Genova, and he studied in collider physics, but then he spent most of his scientific activity on neutrino physics. For instance, he has been spokesperson of the Pallavicini experiment for solar neutrinos and other important rare decay experiments. So we have this slot, and the second one will be in the afternoon. There was a rearrangement in the schedule, so all the neutrino phenomenology will be covered today. Thank you.
Thank you, Marco, and thanks to all for being here. So I will essentially give a lecture on neutrino phenomenology from an experimental point of view, focusing on the neutrino properties, on their interaction with matter relevant for the construction of experiments and relevant for the different measurements. I will go through many, not all, experimental techniques, certainly the main one. And let me clarify that, of course, I will go quickly 4 hours through a huge amount of information. So clearly, not all the slides will be analyzed in detail. They are given for reference. So sometimes I will be fast. If I go too fast, you tell me. It's very important because it's not the first time I give this lecture. Sometimes I've heard complaining, so the red part is important. I am not listing all the experiments, but the fact that some experiment is not mentioned does not mean it's not important. I pick some examples to identify some techniques, but of course I'm not mentioning all neutrino experiments, and the lack of that, particularly if it is yours, does not mean that I don't like it. So history, very quickly. We know, you know, I'm sure, that neutrino physics comes from the study of radioactivity, and particularly from the study of so-called beta decay, which is the emission of an electron from the nucleus. Since the beginning, a few problems arise. The first one was the energy spectrum. The electron energy is continuous, which is not consistent with the two-body decay. And more recently, in terms of time, so the early 19th century was the energy problem. At the end of the 20s, it was also possible to study spectroscopy the spin of nuclei. And it was understood that in some cases you had a problem with angular momentum because, for example, carbon-14 is a boson, nitrogen-14 is a boson, and if you have an electron, you have a problem. Of course, again, I go through some experimental facts mainly to teach you something and not to make history. So I think it's important that you understand, that we understand, is that this problem was not easy at all. The problem was difficult because natural radioactivity is not a clean thing. We will hear on many experiments that many radioactive backgrounds to, for example, neutrino and double beta decay, but also dark matter surge, solar neutrinos, come from uranium and thorium chain. You have the uranium chain as an example there. As you see, it's a mess. It's not an easy thing. It's not such a thing as a pure natural radioactivity. Most of the time, the alpha, beta, gamma are mixed. You have alpha particles, you have beta particles, you almost always have X-rays from atomic spectroscopy, and you have gamma rays from nuclear reactions. If you also discover the neutron, you have another element that you have to take into account. These are relatively easy to distinguish, but you have to understand that the propagation of these things into matter. Alpha rays, as you know, are absorbed very easily. Beta are a little bit more capable to penetrate matter, but it's still a matter of millimeters of meters. You go to centimeters or meters for X and gamma rays, and you go to several meters for neutrons. But all this radioactivity is absorbed in a relatively small amount of matter. Again, quickly on history, we know that the solution came in 1930 with the Pauli proposal of adding another particle to the scenario. This was a big thing. Now it's you heard from Marco Cirelli that theoreticians like a lot to postulate the new particles. They don't refrain from doing that. But that was not the case in 1932. At that time, only the nuclei and the electron were known, essentially the proton and the electron. In 1932, there was the neutron, but matter was a simple thing. Postulating something that you don't see, nobody have heard of, and it's particularly something that you don't see and probably you cannot detect. was a big step. This must be also included in the fact that the neutrino theory comes together with the first true quantum field theory, the first theory in which it is assumed that matter is created from vacuum and not simply part of existing matter. Neutrino is not a supernuclear particle. It was thought to be that at the very beginning by Pauli, but it was quickly understood that it's not. It's something that comes out of vacuum due to a new interaction, that is weak interaction. Of course, the theory had immediately some success, so it became the baseline of the weak interaction. Fermi theory almost killed the neutrino physics from the very beginning. Even this, I assume it's rather well known. It was Bethe, Hans Bethe, who performed the first calculation of electron neutrinos. Now we call it electron neutrino, but at that time was simply the neutrino. That cross-section is exceedingly small. It's 10 to the minus 42, 10 to the minus 44 square centimeter at 1 MeV, depending if you interact with the nuclei or with an electron. This means that if you do the quick calculation, you see that the mean free path of a neutrino in matter is gigantic, and essentially there is no hope to detect a single neutrino. We can do neutrino physics, but not pinpointing on a single neutrino. That's impossible. You can get some events if you have a huge flux to compensate this immensely small cross-section. Essentially, no materials stop neutrinos except two cases. One case is if the neutrino energy is immensely large. We have some examples from astrophysical neutrinos, and only in that case the Earth, as we will see, it's not anymore transparent, but otherwise even a planet is transparent to neutrinos. This is a very important thing. Unless you go to a neutron star that is dense enough to stop neutrinos, but this is a very specific topic. I assume you will get some lectures on that. The historically most important process to detect neutrinos is the inverse beta decay. It's essentially the reverse beta decay, in which you have what we now call an antineutrino. I will comment on that, but let's assume we understand what we mean, and it is absorbed either by a nuclei or by a proton. If in the Rhine's-Cohen original technique, it is a proton. The proton becomes a neutron, and then with the emission of positron from vacuum. Why this is very interesting? Because you have two signals. One is the so-called prompt signal, in which the positron is emitted, can be detected by itself, and then annihilates with another electron, giving two gamma rays. This is a very fast thing. In a few nanoseconds, the positron will stop and will emit the two photons. That's what we call it, the prompt detection. You cannot distinguish the propagation of the positron between the two emissions. It's too fast. So you don't see first the propagation and then the two photons. You see the whole thing together in a prompt event a few nanoseconds after the absorption. But then you have a neutron. The neutron will propagate. The neutron will be a slow particle. It has a strong interaction, but the cross-section for a neutron to be captured by another proton is not that large. So the neutron will survive a long time. What I mean with a long time, a few hundred microseconds in a typical material. It's 250 microseconds in a liquid scintillator. Can be higher or smaller depending if you add something that has a better neutron capture cross-section. For example, you can add the cadmium, you can add the boron to improve the capability to capture the neutron. But anyway, this will be a slow process. So you have one signal from the positron and one signal from the neutron. Which signal will depend on the material? You can get Cherenkov light if you use water. You can get scintillation light if you use a scintillator or liquid argon or liquid xenon or anything in which scintillation light is there. You could use a crystal to detect, again, either Cherenkov or scintillation light. This is general, but the process, the physical process, is very important. This ping pong, in which you have one fast and one slow. It's called the delayed coincidence. And it's very powerful because this double signal is a strong signature of the existence of the antineutrino capture. It is this way. Now I go faster because I assume you know. Renscoe 1956, using the large flux of the neutron reactor. I said Hans Bethe almost killed the neutrino physics in 1934, true, because at that time it was simply unthinkable to detect antineutrinos with that cross-section. But then the war came, nuclear reactors came, and the very strong neutrino source became available, the nuclear reactor, which was the first source to be used. Closer to a nuclear reactor, you get about 10 to the 20 neutrinos per gigawatt per second, which is, of course, an immense flux. It is about 100 times bigger than what we get from the sun, and it's made of relatively high energy antineutrinos that are the easiest thing to detect. So first, we learn about neutrinos using reactors, and after that, another important source of neutrino became the sun, but it took longer for two reasons, because the flux is lower, but also because you don't get antineutrinos from the sun. You get neutrinos, and the neutrinos are harder to detect, so it's more difficult to detect solar neutrinos than reactor neutrinos. Again, I don't want to make history, but Renscoe 1 were the first to understand that if you want to do neutrino physics, you better go underground. It's not necessary to go underground for all neutrino physics. There are some experiments that can be done not underground, but most of the experiments benefit from going underground. The reason is simple. We have a huge amount of cosmic rays, and about 200 per square meter per second. Think of these numbers and compare to a few events per day, per hour, per month, per year, depending on the neutrino experiment, but there is always at least 6, sometimes 8, sometimes 10 orders of magnitude between the neutrino expected signal and the background you expect from cosmic rays on surface. So being on surface is bad. It's bad because you have a lot of muons, but it's also bad because you have a lot of neutrons from transplantation and from other activities, and you have a lot of gamma radiation. All this can mimic neutrino interactions in some cases, especially at low energy. And so going underground was learned the hard way, because they started not underground, they failed, and then they understood that they had to go underground. Historically, they used water as a medium. Water is cheap, so we will get water over and over in these lectures, because many experiments are based on water. They dissolved the cadmium in water exactly to favor the neutron capture, and they could, using what we now call the Renscoe technique, the inverse beta decay of antineutrinos on proton, detect a sufficient signal. Using the delayed coincidence, where we were in the 50s, some electronics was existing, but not as fancy as the one we play with today. So it was harder, but it was possible to see into the scope, because what they saw was the track on the scope of the two pulses, one delayed by a few hundred microseconds from the other, and counting this delayed coincidence with the scope, they could prove that antineutrinos were detected from the detector. Very quickly, just not to forget, the very same year in Hungary, there was this picture taken. This is the first picture indirectly showing the existence of neutrinos, because it is the track of the lithium-6 nuclei decaying, it's a helium-6 decaying into lithium-6 with the emission of an electron and the neutrino. This is the first time in which it was possible to measure the track of the lithium recoiling and the electron. It's clear that this is a three-body. Historically, it is relevant because this picture was taken a few days before the Russian invasion of Budapest, and they had to stop. So it was kind of forgotten, but it's important not to forget. They did it for the first time. It's very quickly again, weak interaction violate parity. This was discovered in 1956 by Shangchen Wu, a Chinese scientist, moved into the United States, very bright physicist that for incomprehensible reason was never given the Nobel Prize for this fantastic measurement. It's historical measurement, so I assume you already saw it, but of course it's a big milestone because it proved that weak interactions are special, and therefore neutrinos, which are the only particles sensitive only to weak interactions, are very special, and this is extremely relevant. Why it's relevant? Well, 2 years later, a beautiful experiment made by Goldaber, Grozing, and Suniar proved that due to this parity violation, neutrinos are emitted always with well-defined helicity. I would say chirality, but chirality and helicity are the same only if neutrinos are massless. Neutrinos were thought to be massless at that time, so if you read all the documents, you always see chirality and helicity mixed. But I am assuming you know the difference. In case of massless particles, the two quantities are strictly related. Otherwise, you have to be careful not to mix the two things. The standard model couples chiral states, left and right, but the left-handed chiral state is connected for a very light particle to a very well-defined helicity state. And this experiment, with using these very clever properties of europium-152, nature has been kind for us because there is only one nuclide that allows to do that, and this is europium-152 metal stable state, in which, thanks to this mixture of angular momentum conservation, helicity conservation, it is possible essentially to bring the original neutrino helicity to a photon helicity and then measure the photon helicity. And the experiment allowed to prove that all neutrinos emitted by the europium-152 have a very well-defined helicity in one only direction, and they are left-hand. Let me comment on this, because this is related to something we still don't know. Neutrinos are always created left-handed because, as we will see in a moment, the standard model couples only left-handed component of the neutrino to the Z or to the W. We normally called antineutrinos the other right-handed component, but this is not obvious. It is obvious in the sense that it is irrelevant if the mass of the neutrino is zero, because as I said, helicity is conserved and you have a clear correspondence between helicity states and chirality, and there is no problem. But if mass is not zero, and now we know mass is not zero, although we don't know the number, you can ask yourself a question. What happens if I follow a neutrino, I run faster, and I go faster than the neutrino? I make a Lorentz transformation, and I look at a neutrino emitted by a double beta decay. By switching the helicity, because I run faster, I change the sign of the momentum. The angular momentum will not change for a boost. And this question is perfectly sensible. What is the answer? We don't know. Because this is indeed at the heart of the difference between neutrino being a Dirac master-driven particle. So the master follows what is dictated by the Dirac equation, or you have a neutrino that is so-called Majorana neutrino. If you follow and go faster than the Majorana neutrino, you will see an antineutrino, or you will see what we call an antineutrino. Be careful. The Majorana particle has no charge. It's perfectly neutral. So the antiparticle coincides with the particle, and the two states that we normally call neutrino and antineutrino are simply the two helicity states of one spin 1/2 particle. If, on the other hand, you see a right-handed neutrino, you see something that is not coupled to the standard model and you could never observe. If the neutrino is a direct particle, by going faster than the neutrino, you see. This is, in my opinion, the easiest way to think of it without formal thing. If you have a mass, it's perfectly logic to ask yourself what happens if you go faster than the neutrino. Of course, you cannot if the neutrino is massless, because otherwise you cannot run faster than a massless particle, and this does not happen. Another way to see it is that if m equals 0, time is frozen, and you will never switch either chirality nor helicity. One formal slide, not to be developed, I assume you know, but just to remind you what neutrinos are. Spinors are particles of spin 1/2. They are described mathematically by two component objects that are transformed by Lorentz transformation by that spinor transformation that is related to a normal boost by these equations. As I'm sure you know very well, you can put two neutrino components in a single Dirac four-component quantity, transforming again using this picture, and just to remind you the notation. So when I mean a four-component spinor, I mean this object that can describe either an electron and a positron in case of charged particles, or two b-spinor for a neutrino. Of course, these b-spinors could be in some definition that you could assign a two quantity to the neutrino and two quantity to the antineutrino, but you could also assign a two quantity to the right-handed or the left-handed components, and this, as I mentioned before, is not exactly the same in case you are talking about the Dirac or Majorana. Can be proven, because this eventually will come, that you can form 5 bilinears of a spinor with the well-defined properties as a function of a Lorentz transformation. So, with this formalism, you now have what is needed to understand the first attempt made by Fermi, which is the very famous 4 fermion point-like interaction. 4 fermions because you have 4 particles participating to the interaction. Point-like because there is no propagator. Fermi was not stupid. He knew very well what he was doing. He knew that inside that point, there should have been something that he didn't know. But of course, he also knew that if you look at the beta decay, the wavelength of a neutron, proton, electron, and probably also the neutrinos is much bigger than the interaction length. So it was perfectly fine to make an approximation and do a point-like interaction. Fermi knew that the point-like interaction was not the end of the story, it was the beginning. He called it tentativo, attempt, exactly for that reason. But physically, he had a very clear picture. The original Fermi theory assumes vector interaction. That's why in the previous slide, I recalled you what it means to have a vector interaction. The current is constructed using the vector, normal vector part. But of course, you can write the scalar with many other ways. You could mix a 2 scalar interaction, you could mix 2 vector, 2 axial vector, you could mix a tensor with the 2 vectors, and so on. So why he chose that? For simplicity, he said, for analogy with electromagnetic current, more precisely. He was an expert in QED. He gave an important contribution in QED, and he started from an attempt to follow QED structure. That part was not corrected, but of course he could not know, because after the discovery of parity violation, you need to explore other models. After a long work, you find that if you take nuclear decay rates and you compare data with theory, you understand that the right current is the so-called V minus A, vectors minus axial current, in which the vector and axial part are of the very same intensity for the lepton part, while in general they take corrections due to strong interactions in the hadronic part. This is the form that was published by Gell-Mann and Feynman in 58. Sometimes you see this is the simplest generalization of Fermi theory. This is completely wrong. There are potentially 10 terms that are as simple as this one, and it's only data that gives the structure. This is important because, again, quite often you hear statements like the standard model is the simplest theory made by this or by that. This is false. The standard model is a theory constructed on data. Yes, there are some important theoretical prescriptions that comes from theory, but many important choices, for example, the structure of the weak currents, come from data. This is not the simplest current you can write. There are many more. It's data that tells you that there is the right structure. And this is a good lesson, in my opinion, for the future of physics. I mean, you heard about how many models are being explored in terms of dark matter. Marco Cirelli gave the beautiful final slide with all the ideas that are around. Without data, you will never be able to say which is the right one, assuming one of them is right. Important comment that it comes over and over in neutrino physics: lepton are easy, hadrons are hard. Not because of the structure, but because one is one, and it's exactly one, while these numbers must be computed from theory, from low energy hadronic interactions. Usually a harder task, sometimes an impossible task. So either you measure GV and GA, or you don't have an easy theoretical tree. Sometimes you can do interesting calculations, but sometimes you have to rely on data to understand what is the relevance of strong interactions. From Feynman theory, of course, the V minus A structure explained the puzzle that was there for a while. The fact that the pion prefers to decay into muon and neutrino instead of electron and neutrino. If you do the exercise, I'm sure you did in your life at least once, of computing the phase space, you would see that the phase space to electron neutrino is much bigger than the phase space to muon and neutrino. So if the electron and the muon are universally identical particles, why the pions prefer to go to muon and not to electron neutrino? The reason is helicity. The pion is a scalar. If you want to conserve angular momentum, the muon and the neutrino need to have opposite spin. So being the momentum opposite as well, they should have the same helicity, but this is forbidden by the standard model coupling, by the V minus A structure. You have to switch the helicity, and the switching the helicity requires the mass term. The bigger the mass, the easiest is to switch the spin. So the muon can switch the spin much easier than the electron, and this explains the fact that you see the rate is proportional to muon mass. If you add the QED corrections, you get extra factors, but the story is that one. So the pion decay explains very well why. It's also a proof of parity violation, as it is a proof of parity violation, the existence of these decays. Again, This already said, that just for your knowledge, this structure has been tested very precisely by the twist experiment, which is a relatively recent experiment in which 10 to the 10 polarized muons have been studied very carefully. Again, it was analyzed by studying the scalar, pseudoscalar, vector, axial tensor. So forget about standard model, assume all interactions are there. What can I learn? I learned that if I believe in the standard model, these numbers have a very well-defined predictions, and these very well-defined predictions, which for the standard model should be exactly 3/4, rho and delta are very consistent with 3/4 with very high precision. So the structure of the V minus A theory is very well confirmed, even by high precision data. Of course, you may wonder when people started to think of more than one neutrino. The early interactions showed that muon and electrons are similar. Essentially, they have the very same interaction except for a different mass. You could learn by comparing these processes. You can extract the coupling of the electron to matter from Fermi theory of beta decay. Conversi, Pallavicini, and Piccioni showed that the muon are captured by protons with a rate that if you do the calculation with the right quantum mechanics and the mass, it is exactly the same coupling. So the muon capture rate to proton is the same as the electron capture rate to proton, mass corrected. So it's not the same rate, but it's the same coupling if you do the calculation properly. And also, Jack Steinberger in his PhD thesis showed that the muon goes to electron and two neutrinos and not one, because the energy of the emitted electron is not monochromatic. Same story of Pauli again. If you put the things together, you can imagine that muon and electrons are very similar, but then you say, why two neutrinos here and why not muon to electron gamma? This is a very deep question. Even today, there are beautiful experiments studying this decay. This is a very recent number. It's the best number we have today. It's not the 1950 number. Right now, we know that muon does not decay to electron gamma up to that level. Again, I ping pong between past and present. If you look at modern eyes, look at this diagram, why this does not happen? Of course, it's a deep question. Easy answer. These neutrinos cannot be the same neutrino to muon and electron, so there are two flavors. One is coupled to electron and one is coupled to muon. That's the easy, simple answer. When you mix oscillation, it's less trivial because you could have oscillations of this neutrino from here to here, but we will come to that in due time. It was Bruno Pontecorvo to propose that there are two neutrinos, and it was Melvin Schwartz, again, after Pontecorvo's suggestion, to say, let's use pions from an accelerator to understand if the neutrinos emitted by muon decay are the same as the one. Of course, the story is that these two neutrinos cannot be the same particle. But if you think, again, and it's very important because you are the generation that will have to solve the dark matter problem, I hope. What do we know about dark matter? Simple answer. Nothing. We have no idea what it is. We just know it's there. What Marco told you very, very extensively and very deeply is that we have plenty of evidence that something that we might call dark matter is there. We hope it interacts with matter, and this is because we have a job, we needed to bring a salary home, so we assume that there is no interaction with matter, we can do nothing. So we assume there are some interaction with matter, and then that's it. Like matter can be from the sub-micro electron volt up to Planck scale. beautiful experiments are searching in some energy region, but they are just looking around, I would say randomly. Of course, I don't want to be not respectful, because of course there are beautiful ideas and beautiful experiments, but each of them is making a random assumption about where dark matter is, following either some theory or some prejudice. It's important that we understand that it was exactly the same in 1835, and it took almost 100 years to understand, okay? To understand exactly why this does not happen, it took 50 years, not one day. We are now in the same conditions toward another problem, which is another piece of nature that is outside the standard model, and we have to build it step by step, and I'm sure it's gonna take a long time. Again, about history, the first experiment to prove that there are two neutrinos and that these two neutrinos have different interaction is done by Leon Edelman, Malvin Schwartz, and Jack Steinberger, three beautiful persons, three really great physicists, that made this beautiful experiment starting essentially in the 60s. It deserves a little words because a lot of current experimental activities is still based on the very same idea, just made better with more money, with more people, with more technology, but it's still the same. Protons, target, pions, some space to let the pion decay, a muon neutrino and a muon, and you have a muon beam. Of course, nature is kind, but not completely kind. It's not a pure muon beam for two reasons. First, at the level of 10 to the minus 4, the pion will decay into electron neutrino, and this you cannot avoid. So there is an unavoidable contamination of electron neutrinos, but also the protons will also produce other hadrons, chiefly kaons. These kaons, whatever you do, if they have the same momentum, will follow the same path of the pion. And so you will have some neutrinos firing from kaon decay, and this will give you some antineutrinos of both flavors. So you produce a beam that will not be pure, but is highly dominated by muon neutrinos. If you select negative pions, you have negative muon and antineutrinos. If you select positive pions, you have a positive muon and neutrinos. At the very first experiment, there was no pion selection, there was no magnetic field, a simple spark chamber in which you detect a muon. This is a sketch of the apparatus. Of course, what is the signature, which is still an extremely useful tool? The muon is the most penetrating particle, by far. Muon can cross a mountain and reach Gran Sasso Lab and create troubles to Marco looking for dark matter. Can cross very easily tens, hundreds of meters of iron of any material. This is bad in some cases, but it's also good in other cases because it means that if you put a lot of material and you find a very long straight track, it's a muon. Cannot be anything else. No other charged particles can do that much movement inside the dense matter without interacting. The electron will immediately shower, but also another charged hadron will have strong interaction and make a shower that it will be. The electron shower will be like that. I am an experimentalist, so it depends. An electron shower is like that. An hadron shower is maybe 2 meters, 3 meters, if it is very high energy. You learn how to have experimental feelings. Of course, low energy electron shower will be a hand, and the low energy pion shower will be maybe 50 centimeters and so on, but that's the other one. The muon can make 3, 4, 5 meters. No pion can do that. So if you have a good detector, identifying muon is easy. I assume you know Becker-Bloch, but I recall you that the charged particle in matter lose energy by essentially knocking electrons. In most of the medium high energy region, the loss is almost constant. There is a slow logarithmic rise, but it's slow. At low energy, which is particularly relevant for nuclear fragments because are the only cases in which they are slow, but we will see that also muons can be slow, also pions can be slow, and we will discuss. You have the nice 1 over beta square, so you can measure the velocity in this region. You cannot measure easily the velocity here. Essentially, only for the electrons, you have the Bremsstrahlung radiation. Why only? Because the Bremsstrahlung radiation, as you know, is essentially proportional to the inverse of the square mass, and so only electrons can provide sufficient. So the radiation loss by emission of radiation is dominant for high energy electrons, while for other particles usually is negligible. This is the Steinberger, Lederman, and Schwarz experiment. Again, they detected 64 events, 34 events with a single track, 22 with multiple tracks. So making an analysis, they were consistent with 8 electron neutrinos and essentially 34 muon neutrinos. So they could prove that in most of the cases, the pions were providing muon neutrinos. Look at the numbers. It was a dirty experiment. We wouldn't like it a lot today. A lot of mess. Neutrons. 2 electrons directly from the beam, which is not credible because no electron can cross that matter, so they missed something. But of course, Nobel Prize discovery are never so neat because they are the first one. Sometimes they are neat, but usually the message was, is the same neutrino? No, it's not the same. Because the neutrino coming from the pion, most of the cases make a muon, not an electron. If the interaction is the same and the neutrino is only one particle, you have 50% of electron, 50% of muon. That is excluded. That is the discovery. So not always you need a very neat dimension. Hadronic. Leptons have weak interactions, but also hadrons have weak interactions. Many important, interesting things are made with hadrons. As I told you, hadrons are dirty because they, of course, their interaction is not a pure weak interaction. It is also mixed with strong interactions that, especially at low energy, are very difficult to model. We have a beautiful theory of strong interaction, which is called QCD, that of course I am not covering. As you know, QCD is beautifully confirmed at high energy using asymptotic freedom, Spartan model, QCD correction. There are beautiful tests of QCD at high energy. At low energy, things are harder because cannot be treated perturbatively because it's stronger, the coupling constant is large, and there are no methods, essentially, except in a very limited amount of cases, to control low energy, strong interaction. Which means that you have to be careful and in many cases rely on measurement. You have to measure the strong interaction effect in your experiment in order to disentangle the physics you like. Anyway, you see here a classification that is quite standard. You have leptonic decays in which only the initial state is an hadron. You have semi-leptonic in which you have an hadron both in the initial state and in the final state plus leptons. Can also be with 2 hadrons in the final state. You can have oscillations, transformation of an hadron in another hadron through weak interactions, which is of course very important for the kaon cases, but also for the B and D mesons in which oscillations are measured and observed by several experiments. And you have also purely hadronic weak interactions that can be relevant. The structure V minus A is always true, but these operators you cannot even write them usually when strong interaction are included. Very quickly, again, assuming you know, of course, when I say assuming you know, and it's not completely true, you complain, but I assume that all of you, at least once in his or her life, have seen the standard model. So I just recall the basics of the standard model, of course, related to neutrinos only. So neutrinos are part of a fermion doublet of SU2 symmetry. The electron neutrino is paired with the electron, and as you see, there is this big L because only the left-handed component is coupled. The gauge group is a chiral group. It rotates differently the left and the right-handed parts of each four-component fermion field. So that is the symmetry, and that is the baseline of the symmetry. And life is not easy because SU2 symmetry was identified by Glashow in the early 60s. But SU2 alone does not work. You don't get consistent theory. You need another U1 group. So because if you have CSU2, what you would do, that was the initial dream, you have two charge current boson and the neutral one, you interpret it as the electromagnetic one, as the photon. It was the initial dream. But it doesn't work because the W must have a mass, the photon does not have a mass, and there is no way with a single SU2 to build a consistent theory. In order to build a consistent theory, you need another group, and but then, and this is the major contribution of Steven Weinberg, you have to rotate the two neutral components in order to get the right couplings. So you have introduced a rotation that is called the Weinberg angle, and with this magic, you get the right couplings, and you get a theory that is consistent with the data. You don't need to couple the right-handed component, so the so-called weak hypercharge of the right-handed component of the electron is set to 0. Of the right-handed neutrino is set to 0. This is the consistent theory that, of course, has a strong prediction, which is the existence of the neutral current, the weak neutral current that had no experimental evidence until the theory. So this was the first true prediction of the theory. The complete Lagrangian of the standard model, as far as neutrinos are concerned, is this one. Just to remind you the details, what is relevant is that in the standard model you have a charge current interaction, so the neutrinos are coupled to their own corresponding fermion with a coupling that is with the W particle. The weak interaction acts on the lepton part and on the quark part. The quark part is rotated by the so-called CKM Kabilo-Kobayashi-Maskawa matrix, while the lepton part here is still written without the Pontecorvo-Maki-Sakagata matrix mixing, which now we know it is, and we will discuss it later, but this is previous to, this is what you write, not including neutrino oscillations. The fermions are coupled to the Z, all fermions are coupled to the Z, including the neutrino, while only charged particles are coupled to the photon. This makes the neutrino essentially the only particle coupled to weak interactions only. One word about accidental symmetries, because they are relevant. There are a few symmetries that are coming out from that Lagrangian. These correspond to these currents, which formally you can write it this way, J1 and J3, J4, and J5. What are these symmetries? It's a simple calculation, a simple exercise with the standard model. Lagrangian without the Yukawa interaction, so before the symmetry break. One of them is just the gauge symmetry, so we don't care, it's there, and it must be there, it will stay there. One you recognize is the so-called lepton number. The other one is the so-called barrier number. And then there are two additional currents that are not observed. So you do need the UCAV coupling to have a consistency with data. With this Lagrangian, you don't obtain anything. If you add the UCAV interaction, the not necessary currents disappear and the theory is consistent. Three families. I already mentioned that the quarks are mixed by the so-called CKM matrix that was originally postulated with the two families by Nicola Capippo in the 60s, and then generalized to three families by Kobayashi and Maskawa in the 70s. With the three families, you also have a nice mechanism to get CP violation into the standard model, which we will comment later. A very similar thing you can do on the lepton part. It was Pontecorvo to suggest the possibility that also the leptons are mixed as the quarks, and now a lot of things happen which we will discuss later, and I'm sure you will hear in many other lectures, but of course the neutrino oscillation saga is part of this, and we will come later. Big questions about these numbers. As I told you, the baryon and lepton number, as far as the standard model is concerned, are accidental symmetries. Nobody asks for those symmetries. They just come out from the structure of the theories. So the question is, are they true symmetry of nature, or do they just appear in the low energy approximation of the theory? And while we know, of course, that we needed to extend the standard model, likely there is another theory that works at higher energy. Will baryon number and lepton number be symmetries of this higher order theory? This is a deep question. We don't have the answer, but this justifies many searches. We study baryon number by searching, for example, the proton decay, and this is a big topic of many large experiments, chiefly the Kamiokande, Super Kamiokande, and in the future, Hyper Kamiokande experiment, but also Dune will study the proton decay, and the sensitivity will include. About lepton number, the most sensitive way to search for lepton number violation is a neutrino stable beta decay, or by searching to muon, to electron, to E gamma, which are still very important relevant features. This is directly connected to neutrinos. In some sense, also this one, in the sense that I have shown you the diagram in which mu2e can be induced by neutrinos, but if you do the calculation in the standard model, the rate you get of this from standard model is super ridiculous. So you will never measure this 10 to the minus 30, 40, I don't remember, but it's a ridiculous, very super small number. If there is anything at the level of 10 to the minus 15, 16, 17, it implies new physics, maybe supersymmetry, maybe something else, but it's certainly very interesting to look for this quantity. Because yes, they are symmetry, but as I told you, accidental symmetry. It's a technical term. It's a symmetry that were not included into the theory. Nobody thought to force lepton number violation or baryon number violation. They came out of the standard model for independent reasons. Maybe they are true symmetry of nature. In that case, we have a cosmological problem because we cannot explain a Big Bang without the baryon number violation and without lepton number violation, because the lepton number of the universe is likely not to be zero. There are many electrons. It's not a trivial question because we don't know how many neutrinos and antineutrinos are around. So let's not take for granted things. But certainly baryon number is not zero because we have protons and neutrons and not antiprotons and antineutrons. So the baryon number of the universe is not zero, and this calls for an explanation. Likely the electron number is not zero, and this calls for an explanation, but we don't know what is the mechanism that causes that. Neutrino mass, from the experimental point of view, we know that the 3 neutrinos are light. Let me say these are the direct limits. If you kinematically measure the electron neutrino mass, you get less than about 1 electron volt, so it's very light. The kinematic limit of the muon and tau neutrinos are much bigger, not very interesting, because now from oscillations we know that the mass difference between the electron neutrino, the muon neutrino, and the tau neutrino is much smaller than these gaps. So the kinematic limit on the tau neutrino mass, on the muon neutrino mass are not very relevant. The important one is the 1.1 electron volt. Okay. This I already said. So, one comment. Again, sometimes you hear the mass term of the neutrinos is beyond the standard model physics. This is not correct statement. The standard model was built assuming massless neutrino. And the standard model is perfectly consistent with massless neutrino because this is a clear feature of the theory. The mass is not added by a radiative correction. So you have a perfectly consistent theory with massless neutrino. Now we know that neutrinos are not massless, but of course, nothing prevents to add mass to the neutrino exactly as we do for the charge of fermions, because we do not understand either the mass of the electron or the mass of the quarks. What we do is to assume a Yukawa sector. We couple the Higgs bosons to the fermions. You add one constant per mass, so it's not a very clever procedure. You have one parameter per observable, so you're not explaining anything. You are simply showing that adding a coupling of the fermion to the Higgs boson, you create a mass term that is consistent with data, but you have to tune the parameters. So we do not understand masses of any particle. Maybe we understand a little bit the mass of the W of the Z because they come from the Higgs mechanism, but we certainly do not understand in a serious way the masses of the fermions. We could add a Dirac part to the neutrino mass, and that would fix the problem. The reason why, and this is true, there are hints and there are reasons to believe that neutrino masses are indeed connected with non-standard model physics, is that there is the possibility, very serious, that neutrinos are Majorana particles. In that case, you do need a partner of high mass, you need the so-called seesaw mechanism or something like that. You have to go outside the realm of the standard model. I will not, I'm sure you will get some theoretical lectures, Marco. There will be some theoretical lectures on neutrinos. Okay, no, but if you ask, but I'm not a theoretician, so I cannot go too much in details. But the clear message is by itself, neutrino mass is not beyond standard model, but it could be beyond standard model, and there are reasons to believe that it could be beyond standard model. Okay, I have a slide on this, I forgot. So the option one is the perfectly standard one. You add a mass term that is the Dirac one. So exactly what you do for the quarks, you do for the neutrinos, and that is perfectly standard model. Yes, you have a problem. You have to assume that the gauge coupling of the right-handed component is zero, but why not? So there is no inconsistency in putting the Dirac mass term for the neutrinos. While if you put a Majorana mass term, then you have to introduce a new field, and this you have to assume it's very large. And there is this nice mechanism that is called the seesaw mechanism, which if you do the coupling this way, by diagonalizing this matrix, you show that if M is much more than small m, what you get is a very light neutrinos, which is the very light physical neutrino, the one we know, and then another right-handed component that is very heavy, and this clearly calls for beyond standard model physics. This is the calculation I mentioned quickly, and you see this is the famous seesaw mechanism, which people like because it gives at least a phenomenological explanation of why neutrinos are much lighter than other particles. Last couple of slides on theory, but I'm going to finish very soon. But of course, these theoretical elements are relevant to motivate the experiment and the efforts I will speak about. Of course, if you have more than one standard model neutrinos, you can generalize and you can add mixing as you do for the quarks. The simplest thing you can do is with the three standard model neutrinos is to mix them through the so-called Pontecorvo, Maki, Nakagawa, Sakata matrix, which is usually parameterized this way. This is not the typical Mandelstam parameterization used in CKM. The reason why CKM and PMNS are usually displayed in different parameterization is just because for the quarks there is a hierarchy of mixing. The Cabibol angle is large. The coupling between the first and the second family is larger, but the coupling between the second and the third is smaller, and even smaller is the coupling between the first and the third. So typically you use a different parameterization. It's not the case for the neutrinos. So you simply display three angles, and none of these angles is very small. We will see, but theta 2,3 is close to maximal. This is about 10 degrees, and this is about 30 degrees. So none of them is particularly small, and there is no apparent hierarchy between the mixing. The existence of a 3 times 3 matrix offered a phase. As you know, a complex phase in a Lagrangian induces CP violation. So you have a CP violating term in the electron sector through this delta phase. You have an equivalent CP violating phase in the quark sector, which explains a CP violation in the quark in the hadron sector. I am pausing 1 second to see if there are questions, because with next slide I want to start exploring the interactions and start discussing a little bit the way in which we can detect neutrinos. Please.
The slide will see the mixing matrix of neutrino.
This one?
Yes. In this case, we assume Majorana neutrino.
No, this is the same. No, this part is no. In case of Majorana neutrinos, you have 2 additional phases, which are not displayed here, because they are not relevant for mixing and for oscillations. They are relevant only on neutrino double beta decay, essentially. And I will show at the end of next lecture this other.
Okay, thanks.
So I have a question. You put the neutrino mass separated, but we don't know the neutrino mass, right? I think tools like.
Oh yeah, when if you are a theoretician, you don't need to know the truth. So you just call it M and you put it into the Lagrange. You don't know the value. You're right. But the master can be done. I mean, the master can be done this way only.
But it's right. It's real. It's right and experimentally.
Where?
Like tools like.
No, these are limits. These are it's less than. It's not a value. These are the experiment. We know that the electron neutrino is not heavier than 1.1 electron volt, but can be anywhere below. Okay. So yeah, we don't know the mass. It's a true statement, but there are something we know. We know that they cannot be heavier than this. Look at this. And we know the delta M squared. I will show in a moment the numbers we get from oscillations. So we know that the three neutrinos are close together in the region between 0 and 1 electron volt. So they are very light, probably close together. We don't know how much close. It depends on where they are. You can call it a degenerate mass or not a degenerate mass. I will comment later. But anyway, there are all three between 0 and 1 electron.
Maybe, Marco, you can elaborate on why you put the limit on the flavor neutrinos instead.
I will comment later. Yeah. Let me, I don't, that is, because that is the kinematic limit. So the kinematic limit is connected to what you measure with the flavor. What you measure with the oscillations is different, but I will comment later. You should call it M1, M2, and 3, and be aware that the flavor against state are not the mass against state, but I will comment later.
What do we know about how often they oscillate, and can the tau oscillate into the electron neutrino? Or does that have to go through?
We do know that there could be oscillations also in that direction. We will show you when I will discuss oscillations. I will enter.
Can you comment a bit more on the two not observed accidental symmetries? Because you say it's not compatible with mass terms. Like, were they important at one point? Were they
No, they're not important because it's an argument on the fact that you do need the. I mean, if you don't have the mass term, you have a problem with those symmetries. Okay.
More important, it's a quiet vacuum expectation. Then is a different situation.
I mean, if you but if you have the power coupling, those symmetries disappear. So if you use the full standard model, those symmetries are not there.
Also before symmetry breaking.
Yes, because it's simply the Yukawa coupling that kills those products. It's the Yukawa theorem. The Yukawa interaction changes the picture.
I didn't get what do we need the marijuana principle for? So why do we use this all with the seesaw mechanism, and what problem does it solve to maybe see the neutrino as a marijuana particle?
No, there is no reason why we need or not need a Majorana master. What Ettore Majorana showed is that if the fermion is not charged, is neutral, the Dirac theory is not the only one. If you want a conserved current, you end up with a Dirac theory. Period. Particularly, if you have electric charge that must be conserved, which is true for the quarks and for the charged leptons, no way. The only consistent theory with quantum mechanics, relativity, charge conservation is the Dirac equation. Majorana showed that if you assume the particle to be neutral, so you don't need anymore a conserved current, you have another possibility. And it's nature to decide which of the two is right. Then, I am not a theoretician, but most of the theoreticians I have spoken with think that the Majorana option is more natural and more probable. But this is the theoretical prejudice. As an experimentalist, what I learn from theory is that the two options are both okay from the theory point of view, and I need an experiment to disentangle the two. Okay. So the standard model is the one I have shown. The good news is that for neutrino physics, we very rarely need it because in most of the cases, except one that I will mention later, the center of mass energy between the neutrino and the target is always low enough that the low energy effective neutrino interaction neutrino interaction is sufficient. So if you assume that the momentum squared transferred during the interaction is small compared to the W mass, and as I will show, it's almost always the case. You can go back to, let me call it Fermi corrected interaction. It's not anymore the Fermi interaction, it's the Fermi interaction with two important additions, the V minus A structure and the neutron currents. So if you include the V minus A structure and the neutron current, the low energy weak interaction Hamiltonian is that one, with coupling that are precisely predicted by the standard model. And you can do a fields transformation to rewrite it in the second form, which is the one that normally is used to compute experimentally useful cross-sections. In very few cases, you need radiative corrections because neutrino physics is precise, but usually not that precise. To get super high precisions, you need huge statistics, but neutrino matter cross-section is small, so you very rarely get huge statistics. We may get large statistics, but in a relative sense. QED corrections to process are less than 1% effect. It's very rare that you measure a neutrino cross-section at 1% effect. So usually you don't need radiative correction. It's not, sometimes it might be useful to have it, but normally the 3-level low energy effective interaction is sufficient to make a sensible experiment. Neutrino interaction, so let's go a little bit with more usable numbers. You can measure, start with the neutrino electron interaction, which is the simplest. The cross-section reads that way. If your apparatus, detects the electron, you might be interested in the differential cross-section, in which you measure the energy of the electron, while if you don't, you normally care about the total cross-section. The total cross-section, as you know, at low energy is linear with the neutrino energy. These factors are all constants that can be computed. And the number you want to remember is that the cross-section are at 1 MeV of order 1 in units 10 to the minus 44. The maximum is the electron neutrino 2 electron, and the other options give you a smaller number, up to 10% in case of a wrong flavor to the this is an anti-neutrino, it's freaking wrong. As I told you, not very often you need radiative corrections. An example of detecting electron-neutrino scattering is Pallavicini, or anyway, any liquid scintillator detectors, such as Juno, such as other liquid scintillator detectors, in which neutrinos interact with the electrons and scatter. Scattering of a neutrino with an electron in the standard model is driven by two diagrams, one through the W, the so-called charge current interaction, and one through the Z, the so-called neutron current interaction. This means that this cross-section, that's why the cross-section of the electron neutrino with the electron is different from the other flavor neutrino to the electron, because the two diagrams are not the same, and you have also the interference here, so you have to compute the cross-section. let's go back a little bit more to experiments. What does it mean, this? It means that, of course, this process can in principle happen at any energy. So here I mentioned the few MeV electron neutrinos, but you could have the 100 MeV or GeV neutrinos in liquid argon, for example, those of you who work in Icarus or work in Dune. But you could also have an electron in water, and in that case, you have the electron hit and moving into the water and getting Cherenkov radiation, and many other options. You could have in future dark matter experiment, these neutrinos will be a background to dark matter measurement because we'll hit either electrons or nuclei and provide a background to the dark matter search or a fog. Now it's fashionable to call it, but
Also in the present one.
Also in the present one, well, maybe there are still dominant backgrounds, but in some cases, yes, the fog is close to be visible. So we have to learn what the electron hit look like. Well, you remember the beta block. So if you are at MeV scale, your electron will make a few millimeters. In principle, you can detect down to very low energies, so it's a technique that may allow you to detect neutrinos even at very low energies. You have, of course, to be able to see a signal. In case of solar neutrinos, the beryllium-7 neutrinos are monochromatic, so they are one line solar neutrinos, they are monochromatic neutrinos, but what they will give you is a shoulder of the kinetic energy of the recoiled electron that makes a spectrum. So this is what you see in the case of Pallavicini, which is again a measurement with at MeV scale. But you can imagine that if you go in water, it's the same. Of course, for example, boromate neutrinos in water, the energies is somewhat lower, 6, 7, 8 MeV, but the concept is exactly the same. The electron will be scattered by this cross-section. And the same happens in liquid argon, for example. Of course, the electron will just do energy loss by beta block if its recoil energy is a few MeV. If you make a hard knock and you produce an electron that is 20 MeV or 30 or 50 MeV, it will begin to shower and give you a signal that is an electromagnetic shower and not simply a single electron. But your detection technique will still be there. Instead of scattering on a neutrino, you can scatter on a nuclei. In that case, you have to compute the cross-section. The cross-section at relatively low energy is dominated by electron neutrinos simply because you cannot produce a muon or a tau until about 100 or even more MeV. The cross-section is not completely trivial to compute because nuclear effects are relevant, but below 30 MeV, essentially, you can use conserved and partially conserved axial current theory to constrain the cross-section to this formula, which yields essentially this value. So at 10 MeV, the cross-section is about 10 to the minus 41 square centimeter, and it scales like the square. That square is wrong. That square is wrong. Must scale with the energy, not with the square. Oh, no, it's correct. No, it's correct. It's correct because this is the antineutrino, so it's the inverse bit. It's correct. Of course, it's not easy to write formulas in the extended range, so you have the plots that give you the numbers. Neutral currents were the first prediction of the standard model, so it deserves to spend a few minutes recalling how they were measured, because the neutrinos were the key player to discover neutral currents. No doubt, Because of course you can see neutral currents also with electrons. For example, deep in electric scattering experiment of the 60s, in which the electron hit a proton, the interaction of the electron with the proton is mediated both by the photon and by the W and by the Z. So there are weak interactions and there are neutral weak interactions into the cross section. But the electromagnetic counterpart is much bigger. So you need very high precision and you need a good theory to disentangle weak interaction effect from electron scattering on proton. It is possible. It has been done in the 80s and 90s, even with good precision, but it's much harder. If you have a neutrino beam hitting a target, of course, only the weak interaction is active and the elastic scattering of neutrinos is mediated by Z, so the pure neutron current. So essentially, the experiment that you want to do is an experiment in which you send a neutrino beam into a target and you search for collisions of a neutrino with the nuclei without emitting an electron, so no charge current, because the emission of the electron of the muon was already done by Steinberger, Schwarz, and so it was already known the charge interaction of neutrino with the target. You want to have a target that is capable to recognize the elastic scattering of a neutrino with the nuclei. So you see only the hadronic component, the nuclei is broken by the neutrino, and you see the effect. To do that, you need a good detector that is capable to show you the event very precisely. And this was done with the bubble chamber. At that time, what was the largest bubble chamber ever built with the liquid freon at 1.5 gram per cubic centimeter. Today it would be environmentally impossible to use such an amount of freon because now it's outlawed. But at that time, there was no the problem was not recognized yet, and it was used as a beautiful detector. Freon is fantastic for physics. So it's bad for the ozone layer, but it's good for physics. But we have to survive on this planet. The experiment invented a new technology, which is called the magnetic horn, because if you wanted to have a better neutrino beam, you want to focus the pions into a specific direction, and the magnetic horn that are now used in all neutrino beam experiments were invented essentially at CERN for Gargamel experiments. What they saw is a bunch of events like this one. Of course, the neutrino cannot be seen. What you see is an event in which, out of nothing, you have a bunch of either pions, particles, photons, but no electron and no muon. So this is not a charge current neutrino interaction because you don't see neither the electron nor the muon. It must be a neutral current interaction. Of course, almost impossible to recognize it here. It takes a lot of time to learn how to do it, but that was the competence of these people 50 years ago, and we just leave it. They did it right. They run their beautiful Gargamel cloud chamber, and they found a consistent number of events with substantial neutron background, but otherwise they could identify the events. They made a lot of effort to prove that what they were seeing was not induced by cosmic rays, was not induced by too many neutrons, and they were a convincing measurement of the fact that they did see neutron current. They also see charge currents, of course, and the ratio between the charge and the neutron currents gave the first prediction of the theta W, which means the first prediction of the mass of the Z or the W. The SPS machine at CERN the collider was built in the late 70s with some energy because this prediction allowed to infer the mass of the W and the Z and
give the experimentalist a hope to see the W and the Z at the UA1 experiment in 82, 83, 84, which led to the Nobel Prize of Carlo Rubbia and Simon van der Meer. Of course, this was a major discovery. This is the true beginning of the Standard Model. If you look at the literature between 68 and 72, you would see that Steven Weinberg would not have got any position at university because of his citations, because they were essentially zero. Nobody cared about the Standard Model when it came out. It became a sensation when it was clear that the model predicted correctly the existence of neutron current and predicted correctly the range of the interaction as observed. Theta W is a free parameter of the model, so it could be extracted from this neutrino measurement, very important, and this is a key. Let me conclude. I still have 15 minutes before lunch. Before we all collapse, few words about the indications that the neutrinos are three. Two independent evidence came, one from cosmology, which shows, in my opinion, a beautiful unity of science. To make it very short, although it's not very short story, with the simplifying condition of isotropy, homogeneity, thermal equilibrium, and the assumption that the universe, at least in some moment after the Big Bang, was governed by Standard Model particle physics, it is possible, assuming that the expansion is governed by general relativity, to compute the abundance of helium-4. This is so-called primordial nucleosynthesis. The true parameter that governs the abundance of helium-4 is the temperature along the expansion. And the temperature along the expansion is mostly governed by a single parameter, which is universally called eta, which is the fraction of the number of baryons in the universe divided by the number of photons. Essentially, a lot of heat means a lot of photons, and so this is a parameter that governs the temperature. This can be extracted from data, and it's known to be this number, omega b, is the fraction of the baryon mass of the universe. Marco Cirelli discussed about omega. Omega is 1. Partially is we don't know its dark energy. Another partially is we don't know its dark matter. A tiny bit we know its baryons, and that is a small number. H is our knowledge of the expansion rate, which is normally parameterized by these constants in unit of 100 km per second per megaparsec. H is about 0.7, and this means omega baryon is 0.4, 0.04, 0.05 or so. Well, the story that came out in the 80s, which is very important, is that the temperature is governed by the number of degrees of freedom. Think of the relativistic gas. The relativistic gas is made of particles that you can consider massless because you assume the temperature is higher than any mass. So you treat all particles like photons, massless particle with chemical potential 0, and you do the thermodynamic of a relativistic box. You simply have to count the number of degrees of freedom to have the equation of state. And the number of degrees of freedom include the number of neutrinos, and all other particles are known. You assume they are relevant. By the way, you can ask Marco more details. Probably he will talk about it, but dark matter is not relevant here because it's not relativistic. You assume that thermodynamically does not create troubles. Otherwise, you don't know how many degrees of freedom dark matter is putting into there, and the theory becomes more complex. But in the simple approximation in which you assume no other particle is disturbing the thermodynamics, you can extract the number of neutrinos. And the helium abundance is consistent with facts and with the theory if the number of neutrinos is about 3. So the first evidence of 3 families came from cosmology. Don't forget that the standard model does not predict the number of families. The number of families is an arbitrary number. The only limit is 16, because if with more than 16 families, there is no anymore asymptotic freedom in quantum chromodynamics. But this is not a very useful limit because we have 3 and 16 is very far away. But theory does not constrain the number of families by no means. You can put as many as you want, but nature apparently has chosen 3, or at least has chosen 3 coupled to the Z, because that's the correct statement. Because after a few years, it was LEP, the Large Electron-Positron Collider at CERN, which ran from 90 to 2001, which is kind of Jurassic for you, but I was still around in physics. So what was done there? It's a very beautiful measurement. If you have a plus machine that brings you at the Z peak, you can measure the cross section as a function of the energy. And this is the Z mass, and this is the cross section in E plus, E minus. The Z can decay in any couple of fermions, so can go to electrons, to muons, to tau, to any quarks, which collectively you call hadrons, because you simply put the hadron partial width by summing all quarks, 5, not 6, because the top is too heavy, so you have to go up to the B and not to the top, and then you have the number of neutrinos plus the coupling to neutrinos. The coupling to neutrinos is computable. Here I quote the quark-quark cross-section, total at the peak and the bright linear line shape. So you measure how many times you go to 2 electrons, how many times you measure the muons, you measure the tau. By the way, these 3 up to phase space correction are identical, so you can cross-check. You measure the hadron by simply counting how many events have hadrons into the final state, so you can measure the rate of the Z2 hadrons. You measure the total width because this is kinematically done. You vary the center of mass energy of the beam, and you have these points, so the total width is measured. These are measured. You can extract the number of neutrinos. This is very neat, and the result is this number, very precise, much more precise than cosmology. So particle physics confirm that there are 3 light standard neutrinos. Don't forget these 2 words. It's not correct to say there are 3 neutrinos. No, because you are not sensitive to the neutrino if it is too heavy. For example, heavier than the Z, and you are not sensitive if the neutrino is not coupled to the Z. So I tell you because part of research today is focused on the so-called sterile neutrinos. Sterile neutrinos are additional neutrinos that might be mixed with the standard one, but not coupled to the Z, or maybe heavier. We don't know. By the way, L3 made another measurement using QED corrections and got a consistent result. Last slide, very important, but I think 7 minutes will be fine. Very important about experimental technique. So in order to make an experiment, you need a source and a target. Think of this as a general experiment. You have a source in which you wanted to produce neutrinos. Neutrinos, essentially, you have to produce by using some kind of charge interaction. Neutral current interaction are not very useful because you have, yes, you get 2 neutrinos from the Z, but you don't know you got it. So you'd better have something that tells you that the source worked. So in most of the cases, the source will be essentially a W source. Let me be very, very symbolic. Of course, it means that there is a process driven by charge current, can be either a nuclear beta plus or beta minus decay, one example. Can be the decay of an electron or a muon into a nuclei, so a nuclear capture. These are very, electron capture is typical of many radioactive elements, but you can also have muon capture. We'll see a very important example of this, in which you can make a very beautiful neutrino beam by muon capture. Or you make in-flight decay, typically of pions, but you could also have muons, and in a very special case, it was made an experiment also with tau, decaying and producing tau neutrinos. Then the neutrino will propagate on very variable distances. The distance can be an order of 1 Fermi inside the nuclei during neutrino level beta decay. A theoretician will complain of this language because it's not correct that you say it's propagated, it's a propagator, which is not exactly as a free propagation. But it means that the neutrino makes a very short movement in space, and it's again reabsorbed. And this is the minimum considered case, which is much explored. I'm sure you will hear about the neutrino level beta decay, correct? So I don't need to evaluate much, but it's relevant for what I'm saying. The other case, the other extreme is cosmological distances. So this slide is old because I mentioned supernova 1978, which is 50 kiloparsec, but actually now we have cases even more because we detected neutrinos from astrophysical sources that are probably outside our galaxy, so it could be even more. But you can span a huge amount of distances. What happens to a neutrino during propagation? Let me first focus on the interaction. Clearly, you always produce a well-defined flavor at the interaction if you have a charge current, because either you produce an electron or a muon or a tau, and at least at the initial state of your neutrino, it will be a flavor-defined neutrino. But you see the question mark here, because what you will get at the target? This is not a trivial question. Well, a theoretical case is massless neutrinos in which nothing happens because the clock is frozen, but it's not what is physically relevant today because we know mass is not zero. So there are two interesting things that happen that I ask you to think carefully. Depending on your technical ability to manipulate the Majorana and Dirac equation, you can get these results analytically. If not, just believe me. The two equations produce two effects. One is purely kinematical, of the order of m over e, in which the other helicity component is computed. So you start from one end of the neutrino at the beginning, but during propagation, you develop proportionally to m over e, essentially, the other component. This means that in principle, if you have mass, you could observe a neutrino. In case of Majorana neutrinos, you could have an antineutrino becoming a neutrino, being absorbed by a proton and give you a signal. But it doesn't happen. It doesn't happen, and you may wonder why. And the reason is kinematical. The neutrino mass is super light. The energy is always at the level of 1 MeV, 100 keV or so. So this effect is usually negligible. It happens only for Majorana neutrinos, because otherwise what you produce by this M over E effect is the wrong helicity component, which, if you have a Dirac mass term, is not coupled, so you cannot observe. If you have a Majorana, you can develop the other part just kinematically. But of course, you need such a low energy that then you cannot observe over reasonable distances. The only case in which this is relevant is the neutrino double beta decay, in which the distance is very small. But this effect does not depend on the distance, so it doesn't matter that it's small. This component is m over e independently of the distance. And so neutrino double beta decay is super rare because this effect is small, because m is small. But it's there anyway. The other effect, in case of mixing, so if you have more than one flavor that are mixed, there is another change effect, which is the change of the flavor, which proportional to the square of the mass times the length. In this case, the length matters, and the energy. Just a comment. In principle, you could make an Einstein-Podolsky-Rosen long-distance correlation for those who know. But it's very in principle. In practice, no way. Because to do it, you should observe the flavor at the source and the flavor of the target of the same event. This is impossible. As I told you at the beginning, there is no way to detect a particular neutrino. So this is very, very theoretical, but absolutely not possible. Good point to stop. Okay, so first of all,
And I would suggest to postpone the questions to after the lunch break. Maybe you can think about, or maybe we can start at. So we start at 2:30. We can start back from this slide and see if there is any question on this more phenomenological part, and then we will surely go on also on the experience. But it was important in the development of the problem of the school to have this phenomenological part, both on dark matter and neutrino, because many of you are experimentalists, but we want to have solid basis also from this point of view, which is, of course, crucial to understand what we are aiming at. Okay, so now the lunch is when you have breakfast, so a few meters downstairs towards the village. There is the canteen, and then you can have some spare time. We reconvene here at 2:30. You can leave your stuff here.
Io te lascio, io adesso ho osservato lo sharing.
Sì, allora io fermo la registrazione.